Imagine standing on the surface of Mars right now, this very moment. Your boots press into rusty soil beneath an alien sky, and you turn slowly, taking in the landscape that stretches endlessly before you. The horizon curves gently in ways Earth's never does. The sky above is not black, not blue, but a strange butterscotch hue that defies every textbook image you've ever seen. And in that moment of recognition, you realize something profound. Almost everything you were taught about Mars in school was incomplete, not wrong, but carefully simplified, reduced to facts that fit neatly on classroom posters: the rust-colored sphere, the dead planet, the barren, lifeless wasteland waiting in the cosmic dark. But Mars is none of these things. Not really. Not completely. Tonight, we will uncover the hidden layers of the red planet, the secrets that textbooks glossed over, the discoveries so recent and so profound they haven't yet made their way into common knowledge. We will explore a world that once held oceans deeper than Earth's, where mysterious methane blooms in seasonal patterns that scientists still cannot fully explain, where ancient riverbeds carve stories into stone, and where the possibility of life past or present lingers like a whisper in the thin Martian air. If you've ever looked up at that small red dot in the night sky and wondered what it truly holds, this journey is for you. If you enjoy these explorations into the hidden wonders of our cosmic neighborhood, please take a moment to like this video and subscribe. It helps us continue traveling deeper into the mysteries that await. And now, settle in. Let your mind drift beyond Earth. Let curiosity guide you across the void. We are going to Mars, not as it was taught, but as it truly is. Mars has always occupied a special place in human imagination. Ancient civilizations saw its blood-red glow and named it after gods of war. Early astronomers drew elaborate maps of canals they believed crisscrossed its surface, certain that intelligent beings had engineered them. Even when spacecraft finally reached Mars and revealed the truth, no canals, no cities, the fascination never faded. Instead, it deepened. Because what we found was far stranger than fiction. We found a planet that remembers. A world where every canyon, every crater, every dried riverbed holds evidence of a dramatic transformation. Mars was not always the cold, dusty desert we see today. Billions of years ago, it was warm. It was wet. Rivers flowed. Lakes filled and emptied with changing seasons. An ocean, vast and deep, may have covered nearly a third of the planet's northern hemisphere. The water was there. The chemistry was there. And where there is water and chemistry and time, life finds a way, or so every lesson from Earth has taught us. Then something changed. Mars lost its magnetic field. Its atmosphere, no longer shielded, was stripped away by solar wind. The water evaporated or froze beneath the surface. And the planet we see today emerged, a ghost of what it once was. Yet even in this diminished state, Mars refuses to stay silent. Methane appears and disappears in concentrations that geology alone cannot explain. Ancient organic molecules hide in sedimentary rocks. Seasonal dark streaks hint at briny water still seeping from beneath the surface. Mars is not dead. It is waiting. Before we continue deeper into these revelations, I'd like to invite you to share something with us. Wherever you are in the world right now, whatever time it is as you watch this, leave a comment below. Tell us where you're watching from and what hour of night or day it is. Are you drifting into sleep or beginning your morning? Are you alone under the stars or tucked away from the daylight? There is something beautiful about knowing we are all together, scattered across this one fragile world, looking outward toward the same distant planet, sharing the same curiosity that has driven humanity since we first looked up and wondered. Now, let us begin. Let us step beyond the simplifications and into the true Mars, the planet that holds both Earth's past and possibly, just possibly, our future. We have been taught since childhood that Mars is the red planet. Ancient civilizations saw it glowing like a drop of blood in the night sky and named it after gods of war. Romans called it Mars. Greeks called it Ares. Babylonians saw it as Nergal, the bringer of fire and destruction. For thousands of years, humanity has gazed upward and seen red. But what if the truth is more complex? What if the colour we associate with Mars is not the colour of Mars at all, but a trick of perception, atmosphere, and history? The reality is startling. Mars is not primarily red. It is a world painted in shades of butterscotch, grey, blue, green, and purple. The rust-red dust that coats much of its surface is only part of the story, a thin veil that obscures the planet's true chromatic nature. When we see Mars from Earth, we are not seeing Mars as it truly appears. We are seeing it filtered through our own atmosphere, distorted by distance, coloured by expectation. The red we perceive is amplified by Earth's air, scattered and refracted, until the planet glows crimson in our telescopes. It is a cosmic illusion, one so deeply embedded in human consciousness that even photographs from the surface have been altered to match our assumptions. The iron oxide explanation is scientifically accurate but incomplete. Yes, Mars's soil contains oxidized iron, the same compound that creates rust on Earth. This gives portions of the planet a reddish-brown appearance, particularly when dust storms sweep across continents, lifting billions of tons of fine particles into the thin atmosphere. During these global dust events, Mars can indeed appear uniformly red from space. But these storms are temporary. Between them, the planet reveals its authentic palette, one far more diverse and alien than the monochrome desert we imagine. When rovers land on Mars and send back unprocessed images, scientists are often startled by what they see. The rocks are not uniformly red. They are grey basalt, dark volcanic stone, tan sedimentary deposits, and even patches of bluish-grey minerals that hint at ancient water interactions. The sky itself shifts through a spectrum of colours depending on atmospheric conditions. At midday, under the pale sun, the Martian sky appears a dusty butterscotch or yellowish tan, coloured by suspended iron oxide particles. But at sunset, something extraordinary happens. The sky turns blue. This inversion is one of Mars's most beautiful paradoxes. On Earth, our sky is blue during the day because nitrogen and oxygen molecules scatter shorter blue wavelengths of sunlight. At sunset, light travels through more atmosphere, scattering the blue away and leaving reds and oranges. On Mars, the process reverses. The fine dust particles scatter red light during the day, but as the sun approaches the horizon, blue wavelengths dominate the twilight. The result is a sunset glow that appears cool and azure, a phenomenon captured by Spirit, Opportunity, Curiosity, and Perseverance rovers. These images exist, yet they remain lesser known than the red landscapes that dominate public consciousness. Why then does the myth persist? The answer lies partly in history and partly in presentation. Ancient observers had no choice but to see Mars through Earth's atmosphere, which naturally emphasizes red wavelengths from distant objects. The planet's apparent color became inseparable from its identity. When telescopes improved, astronomers continued to describe Mars in red terms because that is what tradition dictated. The name Red Planet became canonical, taught in textbooks, repeated in documentaries, embedded in cultural imagination. But the modern perpetuation of this myth is more deliberate. When NASA and other space agencies release images from Mars, they face a complex choice about color correction. Raw images from rover cameras often look unfamiliar, almost alien, with color balances that seem wrong to human eyes. These images are taken through various filters designed for scientific analysis, not aesthetic appeal. To make the images comprehensible and relatable to the public, NASA often adjusts the colors to approximate what a human eye would see under similar lighting conditions. Sometimes, white balance is calibrated using reference targets on the rovers themselves. However, these adjustments are subjective. Different processing techniques yield different results. Some versions emphasize the red tones, matching public expectations and creating dramatic, Mars-like imagery that reinforces the planet's warrior god heritage. Other versions, calibrated more neutrally, reveal Mars as a world of greys, tans, and muted earth tones, strikingly similar to desert regions on our own planet. The psychological impact of these choices is profound. Red Mars feels alien, hostile, uninhabitable. Grey and tan Mars feels familiar, perhaps even welcoming, a place where humans might one day walk without feeling entirely foreign. Evidence from multiple rovers demonstrates this diversity. Curiosities' traverse through Gale Crater has documented landscapes ranging from dark volcanic sands to light-coloured sedimentary outcrops. Perseverance's exploration of Jezero Crater has revealed blues and greens in certain rock formations, minerals that formed in the presence of water and have retained their distinct coloration for billions of years. The InSight lander's location showed a surface that appeared almost beige, devoid of the dramatic red most people expect. Each mission adds complexity to our understanding of Martian color, yet the simplified narrative persists. The deception, if we can call it that, is not malicious. It is a consequence of translating cosmic reality into human perception. Mars exists independent of how we perceive it. The planet does not care what colors we assign to its surface, but we care. Color shapes our emotional response, our sense of connection or alienation. A red Mars is the stuff of science fiction and conquest. A tan Mars is the setting for future colonization. A blue sunset Mars is a reminder that beauty exists beyond Earth, that wonder is not confined to our atmosphere alone. Understanding Mars's true colors is not merely an exercise in correcting misconceptions. It is an invitation to see the universe as it actually is, rather than as we have been conditioned to imagine it. Every planet, every moon, every asteroid carries within it a palette shaped by billions of years of chemistry, geology, and cosmic accident. Mars's iron oxide dust is real, but so are its grey stones, its blue sunsets, its green-tinged minerals. The red planet is red, yes, but it is also so much more. As we prepare to send humans to Mars, this matters. Astronauts will walk beneath that butterscotch sky and watch the sun set in shades of blue. They will see Mars not through the lens of mythology or image processing, but with their own eyes. And in that moment, the deception will end. Mars will finally be seen as Mars, not as a reflection of ancient fears or modern expectations, but as a world unto itself, complex, beautiful, and waiting to reveal truths we have not yet imagined. The surface of Mars today is a desert, a frozen, wind-swept expanse of rust-colored dust and ancient stone. The air is thinner than Earth's highest mountain tops. The temperature plunges to -80 degrees Fahrenheit on a warm day. Rivers do not flow here. Rain does not fall. The only water visible exists as ice at the polar caps, or frost that briefly appears in the early morning before vanishing into the thin atmosphere. But this was not always the truth. Billions of years ago, Mars was a different world entirely, where craters now dominate the landscape. Waves once rolled across vast open waters, where dust devils spiral through empty valleys. Ancient coastlines mark the boundary between land and sea. Mars, the planet we think of as dry and lifeless, once held oceans deeper than those covering Earth today. This is not speculation. This is not myth. This is written in the geology of Mars itself, carved into canyon walls, preserved in mineral signatures, and measured in the very air that remains. The evidence is undeniable. Mars had oceans, and it lost them. The story of how this happened is one of planetary tragedy, a cautionary tale written in stone and silence. Scientists estimate that approximately 4 billion years ago, Mars harbored an ocean that covered roughly 20% of the planet's surface. This was no shallow sea. Current measurements suggest it was potentially 1.6 kilometers deep on average, deeper than Earth's average ocean depth of about 1 kilometer. To visualize this ancient Martian ocean is to imagine standing on the shores of a world where water stretched to the horizon, where tides may have risen and fallen, where weather systems gathered moisture and released it as rain across a landscape we would barely recognize today. The northern lowlands of Mars, a vast basin that stretches across nearly a third of the planet, shows unmistakable signs of ancient shorelines. Spacecraft orbiting Mars have mapped features that look exactly like coastal terraces, the stepped formations that occur when water levels gradually recede. Valley networks snake across the southern highlands, their branching patterns identical to river systems on Earth, carved by flowing water over countless millennia. Outflow channels, some hundreds of miles long, tell stories of catastrophic floods that would dwarf anything in Earth's geological record. But perhaps the most compelling evidence comes not from what we can see, but from what we can measure in Mars's atmosphere itself. Water molecules are made of hydrogen and oxygen. Most hydrogen atoms are simple, containing just one proton. But there exists a heavier form called deuterium, hydrogen with an extra neutron. This distinction becomes crucial when we try to understand what happened to Mars's water. Regular hydrogen, being lighter, escapes to space more easily than deuterium when a planet loses its atmosphere. Over time, this creates a signature. The ratio of deuterium to regular hydrogen increases as the lighter hydrogen preferentially escapes. When NASA's rovers and orbiters analyzed the Martian atmosphere, they found something remarkable. The deuterium to hydrogen ratio on Mars is approximately 5 to 7 times higher than on Earth. This is not a small discrepancy. This is the fingerprint of massive water loss, a planetary scale evaporation that has been unfolding over billions of years. By working backward from this ratio, scientists have calculated that Mars has lost approximately 87% of its water over the past 4 billion years. 87%. To comprehend this number is to imagine Earth's oceans slowly vanishing, kilometre by kilometre, century after century, until only shallow puddles remain frozen at the poles. What happened to Mars was not a sudden catastrophe. It was a slow bleeding of its hydrosphere into the void of space. But why? Why did Mars lose its oceans while Earth kept its? The answer lies deep within the planet, in a catastrophic failure that doomed Mars' ability to hold on to its atmosphere and water. Earth is protected by an invisible shield, a magnetic field generated by the churning of molten iron in its outer core. This magnetic field extends far into space, deflecting the solar wind, the constant stream of charged particles expelled by the sun. Without this protection, the solar wind would gradually strip away Earth's atmosphere, molecule by molecule, carrying it into space. Our magnetic field is not just a curiosity of physics. It is the reason complex life could evolve on our planet. Mars once had such a field. Evidence from magnetized rocks in the Martian crust proves that early in its history, Mars generated a global magnetic field, likely through the same dynamo process that powers Earth's. But Mars is smaller than Earth. Its interior cooled faster. And somewhere around 4 billion years ago, perhaps slightly earlier, Mars's magnetic field collapsed. The consequences were catastrophic, though they unfolded over geological time. Without magnetic protection, the solar wind began to directly interact with Mars's upper atmosphere. High-energy particles from the sun collided with atmospheric molecules, giving them enough energy to escape Mars's weaker gravity. Slowly, relentlessly, Mars's atmosphere was stripped away. As the atmosphere thinned, surface pressure dropped. Liquid water could no longer exist stably on the surface. The oceans began to evaporate, and that water vapor, no longer protected, was itself carried away by the solar wind. NASA's MAVEN spacecraft, currently orbiting Mars, has observed this process still happening today. Even now, Mars loses approximately 100 tons of atmosphere to space every single day. Over billions of years, this adds up to an entire planet's worth of air and water, scattered across the solar system like cosmic dust. But not all of Mars' water escaped to space. Some of it remains, hidden beneath the surface, locked away in forms we are only beginning to understand. Ground-penetrating radar aboard Mars orbiters has detected vast deposits of subsurface ice, particularly at mid-latitudes. In some regions, this ice extends meters below the surface, preserved in the cold Martian soil, like frozen memories of ancient seas. At the polar caps, layers of water ice mixed with carbon dioxide form deposits kilometers thick, the last visible remnants of a once abundant hydrosphere. Additionally, much of Mars' water became chemically bound into minerals through a process called hydration. When water interacts with certain rocks over long periods, it can become part of their crystal structure. Clay, minerals, which are abundant on Mars, are particularly effective at trapping water this way. Billions of years ago, as the oceans receded and the surface dried, water sank into the crust and reacted with minerals, becoming locked into the very stone of the planet. This water still exists on Mars, but it is no longer liquid, no longer free. It is entombed in rock, waiting. The implications of ancient Martian oceans extend far beyond geology. Wherever there is liquid water on Earth, we find life. From the deepest ocean trenches to underground aquifers, from Arctic ice to scalding hot springs, life adapts and thrives. If Mars had oceans that persisted for hundreds of millions or even billions of years, the conditions for life to emerge may have existed. Those ancient shorelines may have witnessed something extraordinary. Organic chemistry occurring in tidal pools, hydrothermal vents on the ocean floor releasing heat and nutrients, perhaps even primitive microbes clinging to existence in the Martian seas before the Great Drying began. When the water disappeared, any life that existed would have faced extinction, or would have been forced to retreat deep underground, seeking refuge in subsurface aquifers where liquid water might still persist, protected from the harsh surface environment. We do not yet know if life ever arose on Mars, but the fact that it had oceans, deep oceans, for potentially 1 billion years or more, means the question is not absurd. It is scientifically valid, worthy of investigation, and answerable through continued exploration. To understand that Mars once had oceans is to fundamentally reimagine our neighboring world. It transforms Mars from a dead rock into a planet with a history, a biography written in water and wind. It tells us that planetary conditions can change drastically, that worlds can lose their atmospheres, that oceans can vanish into space and stone. It also offers a mirror. Earth too depends on its magnetic field, its atmospheric pressure, its delicate balance of conditions. What happened to Mars reminds us that planets are not eternal in their habitability. They evolve, they change, and sometimes they lose the very qualities that make them capable of harboring life. As we continue to explore Mars, drilling into its surface, analyzing its rocks, searching for signs of ancient water and perhaps ancient life, we are not just studying another planet. We are studying a parallel history, a world that started much like Earth, but took a different path. In the dry valleys and empty basins of Mars, we read a story of loss, of transformation, and perhaps of resilience. The oceans of Mars are gone, but their memory remains, preserved in every dried riverbed, every mineral signature, every molecule of deuterium floating in the thin Martian air. And in that memory lies a profound truth. Water once flowed freely on Mars. Life may have stirred in those ancient seas. And if we listen carefully to what the rocks are telling us, we might yet discover that we are not alone in our solar system's history of life. The desert that Mars has become is only the final chapter. The story of its oceans is still being written, one discovery at a time, as we piece together the lost world that once was. As we continue our exploration of Mars, we arrive at one of the most tantalizing mysteries in planetary science, a discovery so subtle it can barely be measured, yet so profound it could rewrite our understanding of life in the universe. Deep within the Martian atmosphere, in concentrations measured in parts per billion, something appears and vanishes with the rhythm of the seasons. It is invisible to the eye, undetectable to most instruments, and its very existence has divided the scientific community. This is the story of Martian methane, a ghost in the atmosphere, a chemical whisper that might be the voice of life itself, or merely the echo of ancient geology still stirring in Mars's slumbering depths. The first detection came not from Earth-bound telescopes, but from the surface of Mars itself. In 2013, NASA's Curiosity rover, a laboratory on wheels travelling across the rust-coloured plains of Gale Crater, began sampling the thin Martian air. What it discovered was unexpected. Methane, a simple molecule composed of one carbon atom and 4 hydrogen atoms, was present in the atmosphere. But this was no steady background hum. The methane appeared in sudden spikes, surging to levels several times higher than normal, only to disappear again within weeks or months. These fluctuations followed no pattern that aligned with our understanding of atmospheric chemistry. The methane was seasonal, Yes, but its behavior was erratic, almost deliberate, as if something beneath the surface was breathing. On Earth, methane is everywhere. It rises from wetlands, seeps from ocean floors, escapes from volcanic vents, and most significantly, it is produced by life. 95% of the methane in Earth's atmosphere comes from biological sources. Microorganisms called methanogens thrive in oxygen-free environments, from the guts of cattle to the depths of marshlands, producing methane as a byproduct of their metabolism. These organisms are ancient, among the oldest forms of life on our planet, existing long before oxygen filled our atmosphere. When we detect methane, we think of life. It is biology's signature, written in molecular code across our world. But Mars is not Earth. Its atmosphere is less than 1% as thick, composed mostly of carbon dioxide, with only trace amounts of other gases. Methane should not last long here. Ultraviolet radiation from the sun breaks down methane molecules within a few hundred years, a geological blink of an eye. For methane to persist, even in fluctuating quantities, something must be replenishing it, something active, something ongoing. The question that keeps scientists awake at night is this: what is producing the methane on Mars? And could it be alive? The controversy surrounding Martian methane is not about whether it exists. Multiple observations have confirmed its presence. The European Space Agency's Mars Express orbiter detected methane plumes in 2004. Curiosity has measured it repeatedly from the surface. The debate centers on its origin and its meaning. In the halls of scientific conferences, two camps have emerged, each with compelling evidence, each with profound implications. On one side stand those who believe the methane is geological, produced by chemical reactions between water and rock deep beneath the Martian surface. On the other side are those who dare to suggest it might be biological, the waste product of microbial life hiding in subsurface aquifers, protected from the harsh radiation above. The geological explanation is elegant and does not require life. Mars, though cold and seemingly dead on the surface, may still harbour pockets of liquid water deep underground, where geothermal heat keeps ice melted and chemistry remains active. In a process called serpentinization, water reacts with iron-rich rocks in the presence of heat, producing hydrogen and other compounds. This hydrogen can then combine with carbon dioxide to form methane through purely abiotic processes. Similar reactions occur on Earth in deep-sea hydrothermal vents and in the subsurface of other planetary bodies. Jupiter's moon Europa and Saturn's moon Enceladus both show evidence of this type of chemistry. On Mars, ancient faults and fractures could allow this methane to seep upward, releasing it into the atmosphere in irregular bursts that we detect as seasonal spikes. Yet the biological hypothesis refuses to be dismissed. If liquid water exists beneath Mars' surface, and if that water contains the basic chemical ingredients for life, carbon, hydrogen, oxygen, nitrogen, then microbial life could theoretically survive there. These organisms would not need sunlight. They would not need oxygen. They would simply need liquid water, a source of energy, and time. Mars has had billions of years. Deep beneath its frozen crust, shielded from deadly radiation and the vacuum of space, life could have persisted long after the surface became uninhabitable. These hypothetical Martian methanogens would release methane into underground reservoirs, which would slowly migrate upward through cracks and pores in the rock, eventually reaching the atmosphere in the same seasonal patterns Curiosity has observed. What makes the methane mystery so frustrating and so fascinating is that both explanations are plausible. We cannot yet distinguish between geological methane and biological methane based solely on detection. The molecule is identical regardless of its source. To solve this mystery, we need more than measurements. We need context. We need to find the source. Is the methane coming from isolated underground reservoirs, or is it widespread? Does it correlate with specific geological features like volcanic vents or ancient riverbeds? Does it vary with temperature, suggesting thermal processes, or does it fluctuate in ways that match biological cycles? The seasonal nature of the methane adds another layer of complexity. During Martian spring and summer, when temperatures rise slightly, the methane levels increase. During fall and winter, they drop. This pattern could support either hypothesis. Warming temperatures could trigger increased geological reactions as subsurface ice melts and water becomes more mobile. Or warming could stimulate biological activity, just as microbial life on Earth becomes more active in warmer conditions. The methane appears and disappears as if on a schedule known only to Mars itself, a planetary rhythm we have only begun to perceive. The scientific community remains deeply divided, not out of stubbornness, but out of caution. The claim that life exists on another planet, even microbial life, is perhaps the most extraordinary claim in all of science. It requires extraordinary evidence. Some scientists argue that we are too quick to invoke biology when perfectly good geological explanations exist. They point to the lack of other biosignatures, no organic compounds in concentrations that would suggest abundant life, no isotopic ratios in the methane that clearly indicate a biological source. Others counter that absence of evidence is not evidence of absence, that we are sampling only the tiniest fraction of Mars's surface, and that life, if it exists, is likely hidden far from our reach. What is certain is this: the methane is real. It is being produced now, not eons ago, and its presence suggests that Mars is not as geologically or perhaps biologically dead as we once believed. The planet we thought was a frozen relic of the early solar system may still be active in ways we are only beginning to understand. Whether the source is chemical or biological, the discovery of methane means Mars has secrets still unfolding, processes still operating, mysteries waiting just beneath the dust. Future missions are being designed specifically to investigate the methane mystery. Rovers with more sophisticated instruments capable of analyzing the isotopic composition of methane molecules could provide crucial clues. Drilling missions could reach deeper into the Martian subsurface, directly sampling underground water and rock where the methane originates. Orbital missions with enhanced sensitivity could map methane plumes in real time, tracking them to their sources with unprecedented precision. Each answer will lead to new questions. Each measurement will refine our understanding. But the ultimate question, are we alone in the solar system, hangs over every observation. The mystery of Martian methane is not just a scientific puzzle. It is a meditation on the nature of discovery itself. We search for life on other worlds, knowing that the answer, whether yes or no, will change us forever. If the methane is geological, we learn that Mars is a dynamic world still capable of surprising us, a laboratory for understanding planetary processes that continue long after a planet's surface appears dormant. If the methane is biological, we learn that life is not unique to Earth, that the spark of biology can ignite wherever the conditions allow. and that we are not alone, even if our neighbours are microscopic and hidden miles beneath frozen ground. As Curiosity continues its slow journey across Gale Crater, sampling the air with each passing season, the methane continues its ghostly appearances. It rises from invisible sources, drifts through the thin atmosphere, and dissipates into the Martian sky. It is a signal, faint but persistent, calling to us across millions of miles, inviting us to dig deeper, to look closer, to ask bolder questions. The methane of Mars is more than a molecule. It is a possibility. And in the search for life beyond Earth, possibility is everything. Mars is not alone in its orbit. Circling the red planet are two companions. Two small worlds caught in a slow cosmic dance that will not end peacefully. Their names are Phobos and Deimos, fear and panic, named after the twin sons of the god of war. But these are not moons in the way we imagine moons. They are not spheres. They do not glow serenely in the Martian night. They are irregular, potato-shaped fragments of rock, tumbling through space as if the universe itself could not decide whether they belong to Mars at all. And the truth is, they may not have. More remarkably still, both of these moons are doomed. One will be torn apart. The other may escape into the void. The story of Mars's moons is not one taught in classrooms, yet it reveals something profound about the impermanence of even celestial bodies, about how planets capture, hold, and eventually lose the objects that orbit them. Phobos, the larger and closer of the two moons, is falling. Not slowly, but inevitably, spiraling inward toward Mars at a rate of about 6 feet every century. This may seem gradual by human standards, but in cosmic time, it is a death sentence. Within 50 million years, perhaps sooner, Phobos will descend too close to Mars's surface, crossing what is known as the Roche limit, the boundary where a planet's gravitational pull becomes stronger than the forces holding a moon together. When that moment arrives, Phobos will not crash intact into the Martian surface. It will be torn apart, shredded by tidal forces into a ring of debris that will encircle Mars like a ghostly echo of Saturn's rings. For a brief period in Martian history, perhaps lasting tens of millions of years, Mars will be adorned with a band of shattered rock and dust. Then, slowly, these fragments will rain down onto the planet's surface, and Phobos will be erased from existence entirely. A moon that has circled Mars for billions of years will become nothing more than craters and cosmic dust. Deimos, the smaller and more distant moon, faces a different fate. While Phobos falls inward, Deimos drifts slowly outward, gaining altitude at a nearly imperceptible rate. Current models suggest that in the distant future, Deimos may escape Mars's gravitational hold altogether, becoming a rogue asteroid wandering the solar system once more. If this happens, Deimos will join the countless other fragments drifting between planets, a moon that was briefly tethered to a world, only to return to the solitude of space. The irony is striking. Mars, which may have captured these moons from the asteroid belt millions or billions of years ago, will lose them both. One will be destroyed, the other will flee, and Mars will be alone once again. Neither Phobos nor Deimos looks like what we imagine a moon should be. They are not spheres like our own moon, smoothed by gravity into a perfect form. Instead, they are lumpy, irregular, cratered masses that resemble potatoes more than celestial objects. Phobos measures roughly 17 miles across at its widest point, while Deimos is even smaller, just 9 miles in diameter. Both are heavily scarred by impacts, their surfaces dark and ancient, coated in a fine layer of regolith, the powdery dust that accumulates over eons of bombardment by micrometeorites. To stand on the surface of Phobos would be to stand on a world so small that gravity barely holds you down. You could leap high enough to reach escape velocity, drifting away into space with a single jump. The horizon would curve sharply in every direction, and Mars would dominate the sky, filling half your field of view, a looming rust-red sphere so close you could feel its presence. The origin of these moons remains one of the great mysteries of planetary science. Textbooks often present a simplified narrative, suggesting that Phobos and Deimos are captured asteroids, objects that once wandered the asteroid belt until they were ensnared by Mars's gravity. This explanation is tidy and plausible. Both moons have compositions similar to carbonaceous asteroids, dark, carbon-rich bodies common in the outer regions of the asteroid belt. Their irregular shapes and cratered surfaces support the idea that they are ancient fragments left over from the solar system's formation. Yet capturing an asteroid is not as simple as it sounds. For Mars to have captured not one but two moons, and for both to have settled into relatively circular, stable orbits, requires a series of extraordinarily unlikely events. Gravitational capture typically results in highly elliptical orbits, or the object simply swings past the planet and continues into space. Something more must have happened. An alternative theory suggests that Phobos and Deimos formed from debris ejected during a massive impact on Mars itself. Billions of years ago, a large asteroid or comet may have struck the planet with such force that material was blasted into orbit, where it coalesced into the two moons we see today. This would explain their circular orbits and their proximity to Mars' equatorial plane. However, their composition does not perfectly match Martian surface material, leaving the question unresolved. Perhaps the truth lies somewhere between these explanations. Perhaps Phobos and Deimos are hybrids, fragments of both Mars and the asteroid belt, shaped by collisions and captures across billions of years. The debate continues, and every new mission to Mars brings us closer to understanding the origin of these enigmatic companions. One of the strangest aspects of Phobos is its motion across the Martian sky. Unlike our moon, which rises in the east and sets in the west, Phobos rises in the west and sets in the east. This is because Phobos orbits Mars faster than the planet rotates. A full orbit takes just 7 hours and 39 minutes, meaning Phobos completes more than 3 orbits in a single Martian day. To a hypothetical observer standing on Mars's surface, Phobos would appear to race across the sky, rising and setting multiple times each day, moving in the opposite direction of the sun and stars. It would not linger like Earth's moon, serene and unchanging. Instead, it would streak overhead, a dim, grey shape hurtling through the heavens, a reminder that not all moons follow the same celestial rules. Adding to the mystery are the strange grooves that cover Phobos's surface. These parallel lines, some hundreds of feet wide and miles long, crisscross the moon in patterns that scientists still struggle to explain. Some researchers believe the grooves are fractures caused by the tidal stress of Mars's gravity, slowly pulling Phobos apart, a preview of its eventual destruction. Others suggest they are crater chains, formed by debris thrown up from ancient impacts that recollided with the surface. Still others propose that the grooves are the result of rolling boulders, ejected from impacts and tumbling across the low-gravity landscape, carving tracks as they went. Each theory has merit, yet none fully accounts for all the groove's characteristics. The mystery deepens when we consider that some grooves seem to radiate from the largest crater on Phobos, a massive impact scar named Stickney, which is so large that the collision nearly shattered the moon entirely. The grooves may be scars from that near-death experience, frozen into the surface as evidence of a catastrophe that Phobos barely survived. The fate of Phobos and Deimos tells us something profound about the evolution of planetary systems. Moons are not permanent fixtures. They're captured, they drift, they collide, they are torn apart. The solar system is not static, but dynamic, a place where even the companions of planets are temporary, their existence measured not in eternity, but in epochs. Earth's own moon is slowly drifting away from us, receding at a rate of about 1.5 inches per year. In the distant future, billions of years from now, our moon may appear smaller in the sky, its tides weaker, its presence more distant. Meanwhile, Mars is losing its moons now, on timescales that are, cosmically speaking, immediate. Phobos will be destroyed within 50 million years, a mere blink in the life of a planet. As we study these doomed moons, we are reminded that the universe is not built to last forever. Even celestial bodies, which seem eternal from our brief human perspective, are subject to forces that will eventually unmake them. Phobos and Deimos are messengers from the past, fragments of the early solar system that have survived for billions of years, only to face their end in the shadow of the planet they orbit. Their story is one of impermanence, of the slow, inevitable unraveling of gravitational bonds. And yet, in their final chapters, they offer us knowledge, clues to the history of Mars, the nature of asteroid capture, and the mechanics of tidal destruction. These small, irregular, doomed moons are not merely footnotes in the story of Mars. They are chronicles of time itself, written in grooves and craters, spiraling slowly toward oblivion. Rising from the rust-colored plains of Mars, there exists a mountain so immense that it defies every earthly comparison we might attempt. Olympus Mons, named after the home of the Greek gods, is not merely the tallest mountain in our solar system. It is a monument to geological forces so extreme that they reshape our understanding of what a planet can build. At 25 kilometers high, nearly 3 times the height of Mount Everest, this dormant giant pierces the thin Martian sky with such dominance that standing upon its summit, you would be above most of the planet's atmosphere, gazing down at clouds drifting below your feet like ghostly rivers. Yet for all its staggering height, the true measure of Olympus Mons is not found in its altitude, but in its breadth. The volcano sprawls across 600 kilometers, wider than the entire Hawaiian island chain. If Olympus Mons were placed on Earth, it would blanket an area roughly the size of Arizona. The sheer scale breaks our conventional understanding of mountains. We expect peaks to rise sharply, to announce their presence with dramatic slopes and jagged ridges. Olympus Mons does not. Its slopes are so gradual, averaging only 5 degrees, that if you stood at its base and looked toward the summit, you would see nothing but a gentle upward incline stretching to the horizon. The mountain would be invisible to you as a mountain. You would be climbing the tallest peak in the solar system without ever perceiving it as anything more than an endless, rising plain. This is the profound paradox of Olympus Mons, a mountain so colossal that its scale renders it invisible to human perception from ground level. Only from orbit does its true form reveal itself, a massive shield-shaped dome crowned by a caldera so vast it could swallow entire cities. The caldera complex at the summit measures 85 kilometers across, pocked with multiple collapse craters that formed over countless eruptions as magma chambers emptied and the surface above collapsed inward, again and again, like the slow breathing of a planetary giant in deep sleep. The volcano's edges are marked by cliffs that plunge 6 kilometers straight down in places, towering walls of ancient lava flows stacked upon one another, like the pages of a geological book, each layer recording an epoch when molten rock burst from the planet's interior and spread across the surface in rivers of fire. These cliffs alone are higher than Mount Kilimanjaro. They form a defensive rampart around the volcano's base, a boundary between the elevated world of Olympus Mons and the surrounding plains of Tharsis, the volcanic plateau that gave birth to not just this giant, but an entire family of massive volcanoes. The question that haunts planetary scientists is simple yet profound. Is Olympus Mons truly extinct, or does it merely sleep? Evidence suggests that the volcano may have erupted as recently as 2 million years ago, a geological eye blink. Some regions of its surface appear remarkably young, with lava flows that show little erosion or impact cratering, suggesting they formed in what scientists call the Amazonian period of Mars, the most recent geological epoch spanning the last 3 billion years. If Olympus Mons is indeed still geologically active, then Mars is not the dead world we once imagined, but a planet where internal fires still burn, where the heart of a world continues to beat, however slowly, beneath its cold surface. But why could Mars build such an enormous volcano when Earth, a larger planet, has produced nothing comparable? The answer lies in two fundamental differences between our worlds: plate tectonics and gravity. On Earth, the crust is divided into moving plates that drift across the mantle like rafts on a slow ocean. When a volcanic hotspot forms beneath the crust, the plate above it moves, carrying volcanoes away from their magma source. This is how the Hawaiian Islands formed, each island a volcano that grew over the same hotspot before the Pacific plate carried it away, and a new island began to form. The result is a chain of progressively older volcanoes, none of which grew large enough to become truly colossal. Mars has no plate tectonics. Its crust is a single, unmoving shell. When a volcanic hotspot formed beneath the location that would become Olympus Mons, it remained fixed in place for hundreds of millions, perhaps billions of years. Eruption after eruption piled lava upon lava, building upward and outward, without interruption, without migration. The volcano grew and grew, fed continuously by the same deep magma source, accumulating mass that would have been distributed across multiple volcanoes on Earth. Mars's lower gravity, only 38% of Earth's, played an equally crucial role. On Earth, gravity limits how tall a mountain can grow before its own weight causes it to collapse or sink into the mantle. On Mars, that limit is nearly 3 times higher. Mountains can reach for the sky without being pulled back down by their own mass. The combination of static crust and weak gravity created the perfect conditions for geological monuments that dwarf anything Earth could produce. The structure of Olympus Mons tells the story of Mars itself. Its slopes are composed almost entirely of basaltic lava, the same dark volcanic rock that forms Earth's oceanic crust and Hawaiian volcanoes. This composition suggests that when Olympus Mons was actively erupting, the lava flowed freely, spreading in thin sheets across enormous distances before cooling and solidifying. These were not explosive eruptions like Mount St. Helens, but effusive eruptions, patient and persistent, where lava oozed from the summit and flanks like blood from a wound, flowing downhill in channels and tubes, sometimes travelling hundreds of kilometres before finally stopping. The caldera complex at the summit reveals a more violent history. Multiple collapse events created a nested series of craters, each one marking a moment when the magma chamber beneath the volcano emptied during a massive eruption, and the ground above fell inward to fill the void. The largest of these collapse craters are over 2 kilometers deep, vast pits that plunge into the volcano's interior. Standing at the edge of this caldera would be like standing at the edge of time itself, peering into the architectural core of a mountain that has witnessed eons of Martian history. From the summit of Olympus Mons, the view would be unlike anything experienced on Earth. At 25 kilometers altitude, you would be above approximately 90% of Mars's thin atmosphere. The sky would fade from the typical butterscotch hue near the surface to a deep purple-black, stars visible even in daytime. Looking down, you would see the curvature of Mars itself, the horizon bending away in all directions. Clouds, when they formed, would drift below you, thin wisps of water ice and carbon dioxide catching the sunlight. In the distance, you might see the other great volcanoes of the Tharsis region, Olympus Mons, Phobos Mons, and Asteroids Mons, 3 siblings to Olympus Mons, each massive in their own right but diminished in comparison to their towering brother. The sheer altitude creates practical impossibilities. If you attempted to land a spacecraft on the summit, there would be almost no atmosphere to slow your descent. Parachutes, so effective in landing on Mars' lowlands, would be nearly useless here. You would have to rely almost entirely on rocket propulsion to touch down safely. Conversely, the thin air means less atmospheric drag. A spacecraft launching from Olympus Mons summit would have a significant advantage, needing less energy to escape Mars's gravitational pull. What does Olympus Mons reveal about Mars's interior? The existence of such massive volcanoes suggests that Mars once possessed, and may still possess, a hot interior capable of generating vast amounts of magma. Volcanic activity requires heat, and heat in a planetary interior comes from 2 sources: the residual warmth from the planet's formation and radioactive decay of elements like uranium and thorium deep within the mantle. For Olympus Mons to have erupted potentially as recently as 2 million years ago means Mars's interior cannot be completely cold and inert. Somewhere beneath the surface, warmth remains. Somewhere, the planet still holds energy from its violent birth 4.5 billion years ago. This realization transforms our understanding of Mars. We tend to think of it as a frozen, dead world, a planet whose geological story ended long ago. But Olympus Mons stands as evidence that Mars may only be dormant, not extinct. The difference is profound. A dormant planet could awaken. Magma could rise again through ancient channels. Lava could flow once more across the Tharsis highlands. Mars could prove to be a world where the fire has dimmed but not yet died, where given enough time, mountains might grow taller still. The volcano forces us to confront the vastness of geological time. Olympus Mons likely began forming over 3 billion years ago and may have continued erupting intermittently until just a few million years in the past. Its construction spanned longer than complex life has existed on Earth. Entire ecosystems rose and fell, continents drifted, ice ages came and went, while on Mars, lava continued to seep from the same volcanic vent, building layer upon layer, growing incrementally taller with each eruption until it became the tallest mountain our solar system has ever known. In the silence of space, Olympus Mons endures, not as a monument to destruction, but as evidence of creation, proof that planets are not static spheres, but living, evolving entities that build and destroy, heat and cool, across timescales so vast they make human history seem like a single heartbeat. This volcano, wider than mountains, taller than the atmosphere, and possibly still alive beneath its cold surface, reminds us that Mars holds mysteries we are only beginning to unravel. And perhaps, in its ancient lava flows and collapsed calderas, we might find clues not just about Mars's past, but about the fiery birth of all rocky worlds, including our own. Time on Mars moves to a rhythm almost identical to our own, yet subtly different in ways that reveal the profound strangeness of a world that is both familiar and alien. A Martian day, called a sol by those who study the red planet, lasts 24 hours, 39 minutes, and 35 seconds. This is not an approximation or a rough similarity. It is an eerie cosmic coincidence that makes Mars the most Earth-like world in our solar system when it comes to the passage of a single day. Of all the planets we could have inherited as our nearest neighbour, we received one whose clock ticks almost in sync with our own. This near-identical day length is not merely a curiosity for astronomers. It is a fundamental reason why Mars remains humanity's most promising destination for colonization. Our bodies evolved under Earth's 24-hour cycle, governed by circadian rhythms that dictate when we sleep, when we wake, when our cells repair themselves. To live on Venus, where a single day lasts 243 Earth days, would be to exist in perpetual confusion, our internal clocks forever broken. To settle on Jupiter's moon Europa, where days are measured in mere hours, would require a complete rewiring of human biology. But Mars offers something different. Mars offers continuity. A sunrise followed by daylight, followed by sunset and darkness, all occurring in a time frame our bodies already understand. Yet those extra 39 minutes change everything. They seem insignificant at first, barely noticeable in a single day, but they accumulate. After just 36 sols, the Martian clock has shifted by an entire day compared to Earth time. Morning on Mars becomes midnight on Earth. The workday on one world begins as sleep descends on the other. For the engineers and scientists at NASA's Jet Propulsion Laboratory, who operate the rovers on Mars, this temporal drift is not theoretical. It is lived experience. When missions like Spirit, Opportunity, and Curiosity landed on Mars, their operations teams made an extraordinary commitment. They agreed to live on Mars time. Each day, they arrived at work 39 minutes later than the day before, their schedules slowly rotating through the full 24-hour Earth cycle. Monday might begin at 9 a.m. By the following Monday, it would start at noon. 2 weeks later, they would report for duty at midnight, working through the Earth night, while their rover explored the Martian day in real time, thousands of miles away across the void. The psychological effects of this temporal displacement are profound. Family dinners shift, sleep schedules fracture. The human body resists the change, fighting to remain synchronized with Earth's rhythms, even as the mind demands adaptation to Mars. Some team members reported feeling perpetually jet-lagged, caught between two worlds, belonging fully to neither. Special clocks were designed to display Martian time, their faces marked with 24 hours and 39 minutes instead of the familiar 24. These clocks became symbols of a new way of existing, a reminder that to explore other worlds is not just to travel through space, but to surrender the familiar flow of time itself. Yet time on Mars extends far beyond the length of a day. Mars experiences seasons, just as Earth does. Its axial tilt is 25 degrees, nearly identical to Earth's 23.5 degrees. This means Mars has spring, summer, autumn, and winter, with polar ice caps that advance and retreat, temperatures that rise and fall, and atmospheric changes that sweep across the planet in predictable cycles. But where Earth completes a full orbit around the Sun in 365 days, Mars takes 687 Earth days, nearly twice as long. Each Martian season stretches across months, the northern winter lasting 154 sols, while the southern summer extends even longer due to the planet's elliptical orbit. This orbital eccentricity creates an asymmetry in Martian seasons that has no parallel on Earth. When Mars approaches its closest point to the Sun, called perihelion, the southern hemisphere tilts toward the star, receiving a concentrated burst of solar energy. Southern summers become intense and brief, while southern winters, occurring at aphelion when Mars is farthest from the Sun, turn bitterly cold and extended. The northern hemisphere experiences the opposite pattern, milder summers and shorter winters. This imbalance drives dramatic weather patterns. Dust storms that begin in the southern hemisphere during its summer can grow so large they envelop the entire planet, turning day into twilight and persisting for months. These are not mere storms. They are planetary transformations, events that alter the very appearance of Mars when viewed from Earth. For future colonists, these extended seasons will define the rhythm of Martian life. Planting cycles will stretch across hundreds of sols. Harvests will arrive not in autumn, but in a season that lasts as long as 2 Earth autumns combined. The psychological impact of living through a winter that extends for 5 Earth months is difficult to imagine. Time will feel different, not just in its measurement, but in its weight. The calendar will become a tool, not just for scheduling, but for endurance. Yet the curiosities of Martian time do not end with days and seasons. Ancient Mars, billions of years ago, rotated faster than it does today. The Martian day was once shorter, perhaps only 20 or 22 hours long. Over eons, tidal forces from the Sun and gravitational interactions with its moons have gradually slowed the planet's rotation, stretching each day longer and longer. This process continues even now, imperceptibly slow but inexorable. A day on Mars is still lengthening, though the change is measured in milliseconds per century. In the deep future, millions of years from now, a Martian day may last 25 hours, then 26, drifting further from Earth's rhythm until the synchronicity we take for granted has vanished entirely. For colonists living on Mars, there will be another temporal phenomenon to contend with, one more subtle and more profound. Communication with Earth operates under a delay dictated by the speed of light. When Mars and Earth are at their closest approach, a signal takes approximately 3 minutes to travel between the two worlds. At their farthest separation, the delay stretches to 22 minutes. This means every conversation with home will be asynchronous, every question followed by minutes of silence before an answer arrives. Real-time dialogue becomes impossible. Emergencies cannot be resolved with immediate assistance from Earth. The colonists will exist not just in a different place, but in a different temporal relationship with humanity, perpetually separated by the unbridgeable gulf of light speed delay. Even relativity plays a role, though subtly. Mars orbits the Sun at an average distance of 142 million miles, compared to Earth's 93 million miles. This difference in gravitational potential means that time on Mars passes slightly faster than time on Earth, though the effect is minuscule, measured in microseconds per year. For practical purposes, it is negligible, but in principle, a person living their entire life on Mars would age ever so slightly more than their twin on Earth, not because of high-speed travel, as in classic relativity thought experiments, but simply by existing in a weaker gravitational field. Time itself flows at different rates across the solar system, a reminder that the universe does not experience a single unified present, but countless overlapping time streams, each shaped by mass, velocity, and distance. The near identity of a Martian day to an Earth day is both a gift and a deception. It suggests that Mars is familiar, that adaptation will be seamless, that the transition from one world to another will be natural. But the extra 39 minutes, the doubled year, the extended seasons, and the communication delays remind us that Mars is not Earth. It is Earth's echo, recognizable but distorted, a world where time moves to a similar rhythm but plays an entirely different song. To live on Mars is to accept this duality, to wake with the sunrise just as we do on Earth, but to watch that sunrise arrive 39 minutes later each day, to experience winter, but a winter that lasts half a year, to send a message home and wait, knowing the answer exists, but has not yet arrived. Time on Mars is a bridge between the familiar and the strange, a reminder that even the most fundamental aspects of existence, the turning of a day, the passage of a season, are not universal constants, but accidents of planetary formation. Mars gave us a day we can live with, but it also gave us a world where time itself must be relearned, where clocks must be redesigned, and where the future will be measured not in Earth hours, but in souls, the heartbeat of another world. In 1976, Viking 1 captured an image that would ignite imaginations for decades. A formation in the Cydonia region of Mars appeared to show a face, humanoid and symmetrical, staring upward from the red surface toward Earth. The face on Mars became legend, whispered about in documentaries and debated in countless articles. Was it evidence of an ancient Martian civilization? A monument built by beings who walked the red sands before humanity even existed? The answer, revealed by higher resolution images from Mars Global Surveyor and later missions, was less dramatic but more honest. The face was a mesa, an ordinary hill sculpted by wind and shadow, appearing face-like only from a specific angle under certain lighting conditions. What seemed like eyes, a nose, and a mouth were merely the play of erosion and human pattern recognition, our brains seeking familiar shapes in random geological features. The face on Mars was not a mystery at all. It was a reminder that sometimes we see what we wish to see. But dismissing the face does not mean Mars lacks genuine mysteries. In fact, the more we study the red planet, the more we discover phenomena that science cannot yet fully explain. These are not fantasies projected onto distant hills. They are real, measurable, documented anomalies that challenge our understanding and force us to ask deeper questions about what Mars truly is. Among the most intriguing are the recurring slope lineae, dark streaks that appear on Martian slopes during warm seasons and fade when temperatures drop. First observed by the Mars Reconnaissance Orbiter, These formations behave like nothing else on the planet. They flow downhill, sometimes extending hundreds of meters, darkening the rust-colored slopes with finger-like patterns that suggest liquid movement. The leading theory is that these streaks are caused by briny water, salty enough to remain liquid despite Mars's frigid temperatures. Yet no direct evidence of flowing water has been confirmed. Instruments detect the presence of hydrated salts, minerals that form in the presence of water, but the water itself remains elusive, vanishing before it can be definitively measured. Are these streaks evidence of subsurface aquifers releasing seasonal moisture? Or are they caused by some other process we have not yet imagined, perhaps involving CO2 frost or granular flow that mimics the behavior of liquid? The mystery deepens with each observation. If water is flowing on Mars today, even in small quantities, it transforms our understanding of the planet's habitability. Liquid water means potential for microbial life, sheltered beneath the surface, surviving in hidden pockets where conditions allow existence. Yet proving this requires more than images. It requires landing, digging, and testing, missions that have not yet been executed in these specific regions. Then there are the spiders, not biological creatures, but geological formations so bizarre they earned the nickname arachniforms, spider-like terrain. Each Martian spring, in the southern polar regions, intricate patterns emerge on the surface, radiating outward like the legs of cosmic arachnids. Some of these formations span hundreds of meters, their channels etched into the ground with startling symmetry. When winter returns, they fade beneath layers of frost, only to reappear the following year in the same locations, as if Mars itself is marking time with seasonal art. The prevailing explanation involves carbon dioxide ice. As sunlight penetrates the translucent ice during spring, it heats the ground beneath, sublimating the CO2 into gas. This gas builds pressure until it explosively erupts through the ice, carving channels as it escapes and carrying dark dust to the surface. The theory is elegant and observations support it, yet the precise mechanics remain uncertain. Why do these formations appear only in specific regions? What determines their exact shapes? Are there variations we have not yet detected? The spiders of Mars are not alive, but they are undeniably active, a reminder that Mars is not a dead world, but one that breathes in its own alien rhythm. Beneath the surface, another mystery pulses through the Martian crust. Strange magnetic anomalies scattered across the southern highlands reveal that parts of Mars once possessed a global magnetic field, much like Earth's. Yet Mars lost its magnetic field billions of years ago when its core cooled and solidified. What remains are fossilized magnetic signatures, rocks that locked in the memory of ancient magnetism, like geological time capsules. But some of these anomalies are far stronger than expected, concentrated in patterns that do not align with simple volcanic activity or impact events. Scientists cannot fully explain why these magnetic striations exist in certain regions and not others, or what processes created such intense magnetization. Some speculate that ancient volcanic activity, combined with a once active dynamo deep within Mars, produced these signatures. Others wonder if asteroid impacts delivered magnetic material, or if unknown chemical reactions within the crust generated localized fields. The magnetic mystery is not just about understanding Mars's past. It is about reconstructing the history of a planet that once resembled Earth, a world with atmosphere, water, and a protective magnetic shield, before something catastrophic stripped it all away. And then there is the Great Galactic Ghoul, a nickname born not from geology, but from tragedy. More missions to Mars have failed than to any other planet in our solar system. The statistical anomaly is so pronounced that engineers and scientists joke, darkly, that a cosmic entity devours spacecraft, bound for the red planet. Roughly 2/3 of all Mars missions have ended in failure, lost during launch, transit, or landing. Some have vanished without a trace, others crashed moments before success. The Mars Climate Orbiter disintegrated in the atmosphere due to a unit conversion error. The Beagle 2 lander reached the surface intact, but failed to fully deploy its solar panels, dying in silence. Russia's Mars program has been particularly cursed, with nearly every attempt ending in disaster. Is the ghoul real? Of course not, but the pattern is undeniable. Mars is extraordinarily difficult to reach and even harder to land on. Its thin atmosphere provides just enough resistance to destroy spacecraft traveling too fast, but not enough to slow them adequately for safe landing. The infamous 7 minutes of terror, the descent phase during which mission control can only wait and hope, has claimed mission after mission. Some attribute the failures to bad luck, others to the immense technical challenges. But the ghoul persists in the minds of engineers, a reminder that Mars does not surrender its secrets easily. Every successful landing is a defiance of cosmic odds. Deeper still, scientists have discovered mineral deposits on Mars that should not exist without prolonged exposure to liquid water. Hematite, jarosite, and sulfate minerals have been found in concentrations that require not just brief moisture, but standing bodies of water that persisted for thousands, perhaps millions of years. Yet the timeline of Martian water is fragmented, incomplete, pieced together from scattered evidence. How did these minerals form? Were they created during Mars' ancient wet period, or do they hint at more recent hydrological activity? Some formations appear to be only a few million years old, geologically recent, suggesting that water may have flowed on Mars far more recently than traditional models predict. The paradox is this: Mars today is cold and dry, its atmosphere too thin to support liquid water for more than moments. Yet evidence of water is everywhere, carved into canyons, pooled in ancient lake beds, locked in polar ice, and hinted at in mysterious streaks and mineral deposits. The planet's story is one of transformation, but the chapters are missing, the transitions unclear. Did Mars lose its water gradually, or did catastrophic events strip it away in bursts? Was there ever a stable climate, or has Mars always been a world of extremes, oscillating between frozen desert and brief, violent thaws? These are the mysteries that keep Mars researchers awake at night, not the face, not ancient monuments or alien signals, but genuine scientific puzzles that resist easy answers. Every new mission brings data, and with that data comes more questions. Why does methane appear and disappear in the Martian atmosphere with no clear source? Why do certain regions show signs of recent volcanic activity when Mars is supposed to be geologically dead? Why do some craters seem to have been filled and emptied repeatedly, as if something cycled through them, carving and eroding in patterns we do not yet understand? Mars is not hiding secrets to frustrate us. It is simply a world shaped by forces that operated on timescales beyond human comprehension, sculpted by processes we are only beginning to decode. The mysteries are not failures of science, they are invitations to explore further, to land in new places, to drill deeper, to look closer. Every unexplained streak, every magnetic anomaly, every impossible mineral deposit is a breadcrumb leading us toward a fuller picture of what Mars was, what it is, and what it might reveal about the nature of planets and life itself. We have debunked the face, but we have not solved Mars, and perhaps that is exactly as it should be. A planet without mysteries would be a planet without wonder. Mars still has both. Mars is not just another world to explore. It is a mirror held up to Earth, reflecting both what we once were and what we might become. When we study Mars, we are not simply examining distant geology or analyzing ancient riverbeds. We are reading a cautionary tale written in rust-colored dust, a story of planetary transformation so profound that it changed a world with oceans and atmosphere into a frozen desert where rivers once flowed, but now exist only as shadows etched into stone. The significance of Mars extends far beyond scientific curiosity. This planet holds answers to questions we have not yet fully formed. It is a time capsule preserving evidence of processes that shaped not just one world, but possibly all rocky planets in our solar system. Mars matters because in its silence, we hear echoes of Earth's possible futures. In its desolation, we see warnings we cannot afford to ignore. Billions of years ago, Mars was not the cold, barren world we observe today. Evidence suggests it possessed a thick atmosphere, liquid water on its surface, and perhaps even conditions suitable for life. Then something catastrophic occurred. Mars lost its global magnetic field. Without this invisible shield, the solar wind, that relentless stream of charged particles from the sun, began stripping away the Martian atmosphere layer by layer, molecule by molecule, year after year, for billions of years. What remains today is less than 1% of the atmosphere Mars likely once had. The rivers dried, the oceans evaporated into space. The climate transformed from potentially habitable to lethally hostile. Earth possesses what Mars lost, a powerful magnetic field generated by our planet's molten iron core. This field deflects the solar wind, protecting our atmosphere and making life as we know it possible. But Earth's magnetic field is not permanent. It has reversed many times throughout geological history, and scientists know that one day, perhaps millions of years from now, it could weaken significantly or disappear entirely. Mars shows us what happens when a planet loses this protection. It is a planetary cautionary tale, a world that demonstrates how fragile the conditions for habitability truly are. By studying Mars, we learn not just about another planet, but about the mechanisms that keep Earth alive. This understanding becomes crucial as we face our own atmospheric challenges. Mars offers a natural laboratory for studying climate change and atmospheric loss on a planetary scale. When we analyze how Mars lost its atmosphere, we gain insights into atmospheric dynamics, greenhouse effects, and the long-term stability of planetary climates. The lessons we learn from Mars help us model Earth's own atmospheric processes with greater accuracy. We cannot recreate a planet losing its atmosphere in a laboratory, but Mars has already conducted that experiment for us across billions of years. Every measurement we take, every sample we analyze, every geological formation we study adds to our understanding of how planetary atmospheres evolve, thin, and sometimes vanish entirely. Beyond serving as a warning, Mars represents humanity's most realistic opportunity to become a multi-planetary species. This is not merely the dream of science fiction. It is an emerging necessity for long-term human survival. Earth faces numerous existential threats: asteroid impacts, climate change, pandemics, resource depletion, and threats we cannot yet imagine. Concentrating humanity on a single world is a vulnerability we now have the technology to address. Mars, despite its harsh conditions, remains the most accessible option in our solar system. It possesses resources we can use: water ice locked in its soil, carbon dioxide in its atmosphere, minerals in its crust. Its day length is remarkably similar to Earth's. Its gravity, though lighter, is substantial enough that we might adapt to it. Mars is harsh, but it is within reach. Current plans suggest that human missions to Mars could occur within the next 2 decades. Space agencies and private companies alike are developing the technologies needed for such journeys. NASA's Artemis program aims to establish a sustainable presence on the Moon as a stepping stone to Mars. SpaceX is building the Starship system, specifically designed for Mars colonization. The concept of permanent settlement is no longer purely theoretical. Engineers are designing habitats that could be built using Martian soil. Scientists are testing crops that might grow in Martian regolith. We are planning not just visits, but the beginning of a second home for humanity. This transition from earthbound species to interplanetary civilization represents one of the most profound steps in human history. The technological advancements required for Mars missions do not benefit only space exploration. They cascade back to Earth in countless ways. Developing life support systems that can recycle air and water with near-perfect efficiency leads to innovations in sustainability technology here at home. Creating lightweight, durable materials for spacecraft advances, materials science broadly. Designing autonomous systems that can operate with communication delays of up to 22 minutes pushes forward robotics and artificial intelligence. Medical research for long-duration spaceflight improves our understanding of bone density loss, muscle atrophy, and radiation exposure, knowledge applicable to treating diseases on Earth. Mars missions are not diversions from Earth's problems, but intensive research programs that accelerate solutions we desperately need. Perhaps the most profound reason Mars matters lies in a question that has haunted humanity since we first looked up at the night sky. Are we alone? Mars once had conditions that might have supported life. Did life emerge there as it did on Earth? If we discover evidence of extinct Martian life, even microbial life preserved in ancient rocks, the implications would be staggering. It would mean that life is not a singular miracle confined to Earth, but a natural process that occurs wherever conditions allow. The universe would suddenly become not just vast, but teeming with possibility. And what if life still exists on Mars today? The mysterious methane signatures detected in the Martian atmosphere could be geological, but they could also be biological. Subsurface lakes of liquid water may persist beneath the ice. In these dark, cold environments, extremophile microbes might endure, hidden from the harsh surface conditions. Finding extant life on Mars would revolutionize biology, forcing us to ask what life truly is and how resilient it can be. It would mean that 2 separate origins of life occurred within a single solar system, suggesting that life might be common throughout the universe. The philosophical and theological implications would reverberate through human culture for generations. Even if Mars never supported life, It teaches us about the conditions necessary for life to arise and persist. As we search for habitable exoplanets orbiting distant stars, the lessons from Mars become invaluable. We cannot visit those worlds, but we can study them through telescopes, analyzing their atmospheres and searching for signs of habitability. Mars provides a reference point, a nearby example of a planet that crossed the threshold from habitable to hostile. Understanding what happened to Mars helps us interpret observations of exoplanets. We learn to recognize warning signs of atmospheric loss, to identify magnetic field signatures, to assess whether distant worlds might support life or once did. Mars becomes our training ground for understanding planetary habitability across the galaxy. The urgency of Mars exploration grows with each passing year. We stand at a unique moment in human history. For the first time, we possess the technology to reach another world and potentially establish a permanent presence there. This window of opportunity is not guaranteed to remain open indefinitely. Economic conditions, political priorities, and global challenges could shift our focus elsewhere. But if we succeed, if we establish a foothold on Mars, we take an irreversible step towards securing humanity's long-term survival. We become a civilization that exists on two worlds, resilient against catastrophes that might devastate one planet but spare the other. Mars matters because it forces us to think in timescales beyond our individual lives, beyond single generations, beyond even the rise and fall of nations. It demands that we consider the trajectory of humanity across centuries and millennia. When we commit resources to Mars exploration, we are investing not in immediate returns, but in the survival and flourishing of our species across deep time. We are acknowledging that our responsibilities extend beyond the present moment, that we owe future generations the opportunity to exist, to thrive, to continue the human story. The journey to understanding why Mars matters is itself a journey of perspective. We begin with curiosity about a reddish dot in the night sky. We progress to scientific investigation, sending robots to analyze its soil and atmosphere. Eventually, we realize that Mars is not separate from Earth's story, but intimately connected to it, a planetary sibling that took a different path, a world that can teach us about our own planet's fragility and resilience. Mars holds both our past, in the form of processes that shaped all terrestrial worlds, and our future, as a destination that could ensure humanity's survival beyond Earth. In the profound silence of the Martian valleys, where dust devils dance across ancient lake beds and the sun sets in twilight blue, we find not just a destination, but a purpose. Mars reminds us that planets are not eternal, that the conditions supporting life are precious and impermanent, and that the universe offers both warnings and opportunities to those wise enough to heed them. The red planet beckons not just as a scientific challenge, but as the next chapter in human civilization, a world waiting to be understood, explored, and perhaps one day called home. As our journey across Mars comes to a close, we find ourselves suspended between two worlds. Behind us lies Earth, familiar and blue, a planet teeming with life. Ahead lies Mars, rusty and silent, a world that whispers secrets in a language we are only beginning to understand. Throughout this exploration, we have peeled back layers of myth and misconception, revealing a planet far stranger and more compelling than what textbooks ever showed us. Mars is not simply red. It is a tapestry of colours ranging from butterscotch to slate blue, a world whose surface transforms with every sunrise and dust storm. We have walked the shores of ancient oceans, deeper than any on Earth, now vanished into the thin atmosphere or frozen beneath the regolith. We have encountered the mystery of methane plumes that appear and disappear without explanation, hinting at either living microbes hidden beneath the surface or geological processes we cannot yet comprehend. Both possibilities rewrite what we thought was certain. We have gazed upon Phobos and Deimos, two irregular moons caught in a slow dance toward their inevitable destruction, perhaps captured asteroids that once wandered the solar system freely. We have stood in the shadow of Olympus Mons, a volcano so immense it breaks the very definition of what planetary geology can achieve, a mountain that stretches beyond the limits of imagination into the edge of space itself. We have measured time on a world where days mirror our own, yet seasons stretch twice as long, where calendars must be rewritten and clocks must learn new rhythms. We have confronted the face on Mars, that haunting illusion that sparked conspiracy and wonder, only to find that the true mysteries of Mars are far more profound than pareidolia. From underground lakes to recurring slope lineae, from ancient riverbeds to magnetic anomalies, Mars presents us with questions that challenge the foundations of planetary science. Every answer we uncover reveals three new mysteries waiting in the Martian soil. Mars matters not because it is a dead world, but because it is a living laboratory. It shows us what Earth might have become if our magnetic field had failed, if our oceans had evaporated into the void. It reveals the fragility of planetary atmospheres, the impermanence of worlds, the thin line between habitable and hostile. Mars is both our past and potentially our future, a mirror that reflects both what we were and what we might become. The discoveries continue even now. As you listen to these words, rovers traverse the Jezero crater, drilling into rocks that may contain fossilized traces of ancient life. Orbiters map subsurface ice, searching for the water that future explorers will need. Scientists analyze data from a dozen missions, each day bringing new revelations that reshape our understanding. Mars is not a static chapter in a textbook. It is an evolving story being written in real time, and we are witnessing its unfolding. This is not the end of our exploration. It is merely the beginning. If you have found wonder in these hidden truths about Mars, if you have felt that familiar pull of cosmic curiosity, consider joining this journey further. Like this video, share your thoughts in the comments below, and subscribe for more explorations into the secrets the universe keeps hidden. Tell us, where are you listening from as you drift towards sleep? Which revelation about Mars surprised you most? Your voice adds to the chorus of explorers, dreamers, and seekers reaching toward the stars. As we close, one truth remains undeniable. Mars awaits. Not as a distant abstraction, but as a tangible destination, a frontier where human footprints will soon mark the dust beside rover tracks. The Martian frontier is not merely geological or scientific. It is philosophical, existential, a threshold between what humanity has been and what it might become. Every fact we have uncovered tonight is a stepping stone toward that future, a fragment of knowledge that brings us closer to the day when Mars is no longer there, but here. The journey continues, the mysteries deepen, and somewhere, beneath the rust-colored sky, Mars waits patiently for us to arrive.